Right, and so your first rule for limits at infinity is that the limit as x approaches positive infinity of any constant divided by x to some exponent is equal to 0 as long as your exponent is positive. And then your limit as x approaches negative infinity of any constant over x to some exponent is equal to 0 as long as x to that exponent is defined at less than 0. Okay, so has everybody got that? Yes? Okay. Alright, so if I look at example 1, I'm looking at the limit as x approaches infinity of 4 minus 3 over x squared. Okay, and one of our first rules of limits that we learned in our first section was that we can break limits up into their pieces. So I'm going to break this up into the limit as x approaches infinity of 4 minus the limit as x approaches infinity of 3 over x squared. So you basically distribute your limit. Okay, and then the limit as x approaches infinity of 4 is just 4. The limit of any constant stays that constant. And then we know that the limit as x approaches infinity of any constant over x to an exponent is equal to 0. So anytime you have a fraction, it's equal to 0. And 4 minus 0 is 4. Okay, pretty straightforward. So if you do the same thing for 1b, the limit as x approaches infinity of 7 minus 1 over x squared. If I distribute my limit, that tells me that the limit as x approaches infinity of 7 minus the limit as x approaches infinity of 1 over x squared. Okay, well the limit as x approaches infinity of any constant stays that constant. So that one will stay 7. The limit of x approaches infinity of 1 over x squared, because you have your x squared in the bottom of your fraction, is equal to 0. And 7 minus 0 is 7. Okay, so now if I look at the limit as x approaches infinity of 2x squared plus 3 over 3x squared plus 1. Because your goal, no, it's not 0. It's definitely not 0. But because your goal is to always get every piece of your limit into a fraction, we're going to divide all of our pieces by x squared because that's our biggest exponent. Okay, and whatever you do to one thing, you have to do to the other. That then cancels our x squareds out of -2 and out of 3. So then I'm left with -2 plus 3 divided by x squared. And 3 plus 1 divided by x squared. And so since we can break this up into our different pieces, I know that I can break this up into the limit as x approaches infinity of 2, or -2, plus the limit as x approaches infinity of 3 over x squared, divided by the limit as x approaches infinity of 3, plus the limit as x approaches infinity of 1 over x squared.
And then the 2 on the right is
These two yet become 0. So the limit as x approaches infinity of any constant stays at constant. So -2 stays -2. The limit as x approaches infinity of a fraction where x is on the bottom becomes 0. The limit as x approaches infinity of 3 stays 3. And the limit as x approaches infinity of 1 over x squared is 0. And we know that -2 plus 0 is -2. 3 plus 0 is 3. So -2/3 is your limit. Okay, let's do one more like that, and then that is the exact same problem. We are not doing that one. I'll make one up. Infinity of we'll do the limit as x approaches infinity of 5x cubed plus 7 divided by 2x cubed plus 3.
Divided by x.
So we'll divide by x cubed because that's our biggest exponent. And then that rationalizes our first two terms, so 5 plus 7 over x cubed, and 2 plus 3 over x cubed. So if I distribute my limit, then the limit as x approaches infinity of 5 plus the limit as x approaches infinity of 7 over x cubed divided by the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 3 over x cubed. Okay, so let's simplify. What's my limit as x approaches infinity of 5? 5. What's my limit as x approaches infinity of 7 over x cubed? 0. My limit as x approaches infinity of 2? 2. And my limit as x approaches infinity of 3 over x cubed? 0. 5 plus 0 is 5. 2 plus 0 is 2. Okay, so limits at infinity, pretty straightforward. You guys are going to work through 887, 9 through 28.